everyone. My name is Gwendoline, so I'm a PhD student at ONERA and AAMS22 in France. And today I will present to you part of my PhD work, which is still ongoing. So on the stability of aluminum alloys under laser powder bed fusion studied via process mapping. So as you might all know, during the LPBF process, there is some rapid laser matter interaction that involves complex hydrodynamic regimes, and so melt pool instabilities, metal vaporization, and things like that. So it's well known in literature that depending on the parameter you use, you can have rolling, humping, that kind of phenomenon. There is also instabilities such as spatters. Many presentation was on spatter yesterday and also today. So basically we know that all of that can have an effect on the part quality and on the productivity of the process. So the motivation in this work were to just try to look as closer as we could to those instability during the process, to try to improve our understanding of those phenomena and to try to avoid the related effect. So to do so, we used what we call an open LPBF cell. So as you can see, it works pretty much at the opposite of a commercial machine. So we don't have a laser moving on the powder bed, but a powder bed moving under a fixed laser. Why do we do that? It's because we want to observe the laser matter interaction with cameras that have a fixed frame reference. So what we do is that we fix the laser and we align the camera with the laser. So you can see here what kind of images we can have. I will describe then how I will analyze this. So of course it's not, we've seen beautiful images today with the X-ray imaging and things like that. In here, the setup is really simple. We can change the laser quite easily, so we can change the wavelength, we can change the spot diameter. We can very easily also change the powder. We don't need much powder to do those experiments, so we can do hundreds of trials very quickly, and so generate thousands of data. So how do I analyze those videos? As you can see on the top, you can see, so it's a collection view, you can see the melt pool stability, so you can determine if you're in a stable mode, in a bulbing mode. I will show you the process map that I tried to draw with that kind of view. On the second type of view, you can see here very well the vapor plume and the spatter, so everything that is ejected. And what I try to do is that I developed a system to detect this spatter and to analyze them. So then I try to do a correlation between these two observations. So here you have an example of different what I call states, region, like a stability thing. So you can see on the here. It's quite a stable state, so we have a stable melt pool, and if we look at the solidified sample in the end, it's quite nice. So all the samples are like 1 centimeter long. So here is an example of stable, here you have an example of humping, and here you have a nice example of bowling mode. So for each point you can see here, it's just a unique set of parameters, so we carry out a lot of analysis. And then with all the point, I do then an extrapolation to have that kind of process map, so I know for each parameters if I am in stable mode, pre-humping mode, humping mode, or boom. So then the second type of analysis, so with the spatter, so videos, as you can see here. So we're developing this PhD, a whole system using machine learning to detect the spatter. So we can have for each image on each movie the number of spatter there, and we don't just detect the spatter, we also try to follow them. So we developed a tracking system, so using the morphology of the spatter and everything, we try to follow them from one image to the other. And so here you have, for example, the cumulative trajectories for each spatter. So in the end, this whole, what we call span system, gives us the number, the size, the speed, and the angle of ejection of each spatter, so we can define some pollution rate, for example. So the first results I'm going to present to you are regarding single scan tracks. So as you can see, we've done, for example, process maps for different aluminum alloys. So here you have an example of process map for classic cast alloys, so aluminum, silicon. And here for an AM alloy, so aluminum alloy design for additive manufacturing, so basically it doesn't have all the volatile elements you can find in the cast alloy, for example. So I precise that they both have the same size range in the feedstock powder. And what we can see is that we clearly have a more stable, a larger stable zone with the AM alloy than for the cast alloy. So that means we can work at higher scan speed than the cast alloy. You can see here that we've come quite high in laser intensity compared to what you can do in machines, and we wanted to try things that are quite outside of the scope of a 3D machine. So as you can see also our diameter, spot diameter is also quite big. We tried different laser parameters. In each case, we always had a more stable zone for the AM alloy. Then for each point you've seen before on the process map, we tried to analyze this pattern. So first we just saw that for each spot size, each speed, and well, every parameter we would have, when we had an increase in intensity, we didn't have a constant increase in the spatter ejection. So we have first an increase, true, when we increase intensity we have more spatter, but then we always had an increase at some point, and we observed that every time. So we try to correlate that with the stable zone we've seen before. So as a reminder, the green thing is stable, the orange is pre-humping, the red is humping. So you can see here, for example, this thing is related to that. So intensity here, intensity on the top here. And so at first we could think, oh, we have the feeling that we see something, like when there is a decrease, there is an instability. But the fact is that we also observe this increase and decrease phenomenon for the stable zone in here. So here we have an increase in spatter and a decrease. So we thought it was not related directly to the pre-humping, humping thing. So I tried to look at another parameter, which was the aspect ratio. And we found that each time the maximum number of ejected spatter, so it's number of spatter per scan centimeter, so it's not per second, it's per scan centimeter. Each time the maximum was reached around the transition between the conduction and keyhole mode, which is defined by the aspect ratio, as you can see here. So, to try to understand that, we thought first that it was just the vapor thing, that, for example, when you have an aspect ratio under 1, you have only the vapor interacting with the powder, and so if you increase the intensity, you increase the vapor, and so you increase the interaction with the powder, and you can see here with the accumulated trajectories. Then when you have a deeper track, you tend to just incline the vapor plume, so you tend to interact also with the melt pool. I noticed I just forgot to tell you that here you have the white thing is the total number of spatter, so the total number of spatter we detected on the videos, and on the black thing is the nauseous number of spatter. So what we define as nauseous is every spatter that has a size above the size of the feedstock powder. So every spatter that is bigger than the feedstock powder. So you can see here that most of the spatters are like feedstock powder, and there is a small amount of spatter that is nauseous to us. So we can think that maybe for when we go to a very high intensity, we would have an effect with the vapor plume, we could be stuck on the keyhole or something like that. And so we really see when we have this cumulative trajectory that the ejected spatter to get more and more inclined as we increase the intensity. So that could explain why we would have less spatter with a very high intensity. So here there is another example of process maps for different scan speed. For example, here it's a higher scan speed than here. We still have the same effect of increase and decrease, and you can see here that if we speak of spatter per scan centimeter, we really see that when we go at a higher scan speed, we have less spatter ejected. We have the same effect there. It's still the aspect ratio around 1 is still at the maximum ejected spatter. And so we try to collect that with the density, the volumic energy density, to try if we change as we're talking at different scan speed, but we didn't see any obvious link between the energy density and the spatter. So then it's again a comparison between the cast alloy and an alloy design for additive manufacturing. We can see that again the maximum is at the transition here, and we can see also that the alloy designed for additive manufacturing seems to generate less pollution, so less spatter generated, but most of all less nauseous spatter, so which could be great for the process. And finally, we wanted to compare, so all of what I presented before were on a single scan track, but of course we know that it's not the reality when we do something in AAM machine, and when we do several tracks, we know that because of denudation, you have less spatter with the following track than on the first one. So we wanted, for example, to observe that. But first of all, we try to compare the process map for stability, and we've seen that when we, so the previous border, you can see our first single scan track, and for the multi-scan track, you have here the new borders. And you can see that there is a stabilization effect when we do multi-scan tracks. So when we do multi-scan, we just have a higher stability. I precise that every time, not to make it quite simple, because I was already making a lot of different parameters. I tried to keep constant the overlaying. So for each parameters, I just checked the size of my track in the single scan thing, and then I adapt the hatch to have a constant 50% overlaying for all the parameters. So first, stabilization effect when we do multi-scan track. And then, so we compared the number of spatters, so for the following tracks here, and you can see that it's quite steady, and that globally the following tracks have always about 70% less spatter than the first track. So it was a constant thing for pretty much all the parameters we did there. So to conclude, we could say that the process map that we've carried out highlight stability zones, so regarding the scan speed, regarding the spot diameter, and also regarding the laser intensity. So I didn't show you all the maps we did, but we've done quite a lot of large DOE. So we can see also that the spatter gives information on powder bed pollution, and so that we try to collect that with the stability maps to see the effect, and we've seen notable differences between AM alloys and cast alloy. So basically all of that could help improve the understanding of the process, and thus further in the work we could try to improve the quality and the productivity in LPBF regarding those process maps and those pattern analysis. I also precise that the number and the size is not the only characteristic I get from the spatter with my system. As I said before, I also have the angle and the speed of ejection. So for example, I can easily have that kind of maps, which is extrapolation of the trajectories of the spatter that I detect, and so I can see where are the spatter falling on the powder bed, so I can see if it's a large polluted area or not. So here, of course, I consider that there is no cross-jet. I only have a homogeneous projected atmosphere, but we can see, for example, how high they're going and try to see how many of the spatters are actually just blown away by the cross-jet. So the future goal would be to link the other spatter characteristic like this one to the process maps also. And also it would be interesting to maybe determine the effect of the composition of, for example, the dedicated AM alloy on these results, because if we can identify which element in the AM alloys is responsible for the low spatter ejection and the higher stability, we could maybe design better alloys for additive manufacturing. So thank you for your attention.